Hello everyone, welcome to our channel Everyday E-Learning. So in today's video of digital logic design, we are going to study about synchronous counters. So a synchronous counter is generally the one which transition occurs with the clock. So the synchronous counter uses flip-flops which are all clocked at the same time by a common clock pulse. That is, the flip-flops inside a synchronous counter will be operated at the transition of a common single clock pulse. So in today's video, we are going to study a 2-bit synchronous binary counter. At first, we will see the diagram of that, and then we'll move on to the timing diagram, followed by the state or truth table of the 2-bit synchronous binary counter. As you can see on the left side of my board, we have two JK flip-flops here. These are JK flip-flops, and the two flip-flops are having a common clock. This clock is common to both the flip-flops. It is connected to flip-flop 0 and flip-flop 1 as well. And these two JK flip-flops being connected with a common clock are considered to be a synchronous counter. Now let us see the clock pulse table or truth table for this counter. We'll take here clock pulse, Q1 and Q0. We'll take the initial position here, and then for the first pulse, second pulse, third pulse, and the fourth pulse. 0 0, 0 1, 1 0, and 1 1. So after 3 pulses of the initial one, it will recycle and reach to 0 again. This is the point where the synchronous counter recycles. As it is a 2-bit synchronous counter, it will recycle at the 4th pulse. If it was of greater bit, it would have recycled at the final bit of that greatest bit available. Now let us match it with the timing diagram. I have taken the timing diagram on the right side of my board, and as you can see from the timing diagram that, let me highlight it. As you can see from here that during the first positive edge transition, Q0 changes from 0 to 1 and Q1 stays to 0. And then during the second clock pulse, it goes down from 1 to 0, and then the Q1 changes from 0 to 1. So in this way, the timing goes on. You can see from the table here that for the initial clock pulse, both are 0 0. And for the first clock pulse, Q1 is 0. For the first clock pulse, Q1 is 0. You can see from here, Q1 is 0. And for the first clock pulse, Q0 is 1, which you can see from here. Consequently, for the second clock pulse, Q1 becomes 1. Q1 becomes 1 for the second clock pulse. You can see from here, the second clock pulse, Q1 is 1. And Q0, you can see from here, is 0. Coming to the third clock pulse, both Q0 and Q1 are having high value or 1 value, and at the final clock pulse, both the Q1 and Q0 are low or 0, and at this position, the flip-flop, at this position, the flip-flops recycle, or it can be said that the counter recycles at this position. So being a 2-bit synchronous counter, the recycling is occurred at the 4th clock pulse. So this is how synchronous counters generally work. The concept is pretty simple. No difficult portion in this one. We shall use these counters to develop more performing or complex circuits in our upcoming videos and lectures. So stay tuned and don't forget to subscribe to our channel. Thank you for watching this video.